Hello and welcome to the screencasting of the arithmetic logical unit. So the first question that you might think of is, what is an arithmetic logical unit? And the answer to that is a unit that conducts logical operations such as addition, subtraction, division, multiplication, and etc. These are only some of many logical operations. And in other words, you can think of them as mathematical calculations. But where do you usually find these ALUs, or these operating units? And they're usually found in the CPUs, which are in the computers. And the tasks of these ALU is to compute the mathematical problems that it is faced with. So for example, take the situation of a calculator in the computer, where 1 plus 1 is inputted in through the computer. And those two informations come to the CPU, and with the help of the ALU, the calculation that it is a 2 comes out of the computer, and it outputs a 2. So the purpose of the ALU is to do mathematical calculations and output its results based on its inputs. So our assigned ALU that was given in class was a 4-bit adder ALU. Now this means that the maximum number that can come out of this 4-bit adder ALU is a 15. And if you add all those 4 bits together, which is 1, 2, 4, and 8, you would get 15 as a maximum number. And the system that this ALU uses is the base 2 system, and not the base 10 that we usually use. And generally, how this 4-bit adder ALU usually works is that there is 2 distinct sets of 3 inputs, and each set is considered one input. So say for example, for the first set we input 3, and then for the second set we input a 5, and then the ALU does some calculations and it outputs, of course, the answer 8. Now because we have 3 inputs for one number, there can be an answer of 4 bits. Now what is the base 10 or the base 2 systems? Now the base 10 that we usually use is that number 10 is the coefficient, and that coefficient is powered by 0, then 1, and then increasingly by number, by ones. So over here we have 10 to the power of 0 equals 1, 10 to the power of 1 equals 10, 10 to the power of 2, 100, and so on. So if we take the example of 27 and get the same number 27 in the base 10 and the base 2 systems. So how many 10s would you want for 27? You would need at least 2. And for how many 1s would you need to get 7? You would need at least 7. And when you add those two 10s and 7 1s, you get 27. Now, for the base 2 systems, the coefficient is not 10, but it is 2. And so, 2 to the power of 0, 2 to the power of 1 is 2, 2 to the power of 2 is 4, and so on. Now, if you want to get also the same number 27, how many 32s would you need? You would need 0, because it exceeds the 27. But you need 1 16, 1 8, 1 2, and 1 1. And when you add all those together, you get 27. And that is how you get the same number for 2 different systems. We must know the materials that are used in the ALU so we can know how it works. So some of the materials that are used are LEDs, light emitting diodes, which are supposed to represent the inputs and the output, and the buttons, which are supposed to be the inputs to represent a 1, which is on, or a 0, which is off. And then there are resistors, which their purpose is to slow down the current of the LEDs and not to let the LEDs burn. And finally, logic gates. Now there are many logic gates that are used in the ALU, and some of them is the AND gate, the OR gate, the NOR gate, and the XOR gate. And of course there are others like the NOT gate and the NAND gate. Now as you can see here, this is the symbol of the gate itself, and this is the truth table of the gate. Now let's take the example of the OR gate. Now for the OR gate, each gate has its restrictions and its requirements. Now for the OR gate, it can only output a 1 when either or both of its inputs contains a 1. However, if neither of its inputs has a 1, then it cannot output a 1. Now, the most important gate that is used in the ALU circuit is the D flip-flop, or in other words, the commercial D flip-flop. The D commercial flip-flop is special because it carries on memory, and that memory itself influences the output in the present or previous input, and the output is influenced based on previous or present inputs. So you can think of this as the memory of the ALU. The commercial D flip-flop has two modes, which is an asynchronous mode and a synchronous mode. Now, the asynchronous mode means that the output of the D flip-flop does not depend on a clock, which also means that the output changes when the input does. So they change simultaneously. Now the synchronous state is different, and it's the opposite of the asynchronous state, because the synchronous state is synchronized in a clock with a clock's beat, and the output relies on the clock's pulse for change. So only when the clock's pulse lets it change will it change. Now this is enough of the materials that are used in the ALU, and now we are going to get into a deeper understanding on the arithmetic logical unit schematic itself. Now it can look a little overwhelming at first sight, but hopefully we will be taking it piece by piece to understand each portion's purpose and function. To start off, we will be learning about the load and the add and the push button. These three are at the bottom of the ALU circuit in the schematic. The load button over here, indicated with the orange highlighter, is a button when pressed loads the inputs that are set in the two inputs. The add button, which is indicated with the green highlight, is the function that adds those two inputs together. So if we had a 1 and a 1 and we press the add button, it would output a 2. And the push button, which is indicated with the blue, is the trigger of the add and the load buttons. Now the second thing we're going to look at is the first set of inputs, which is a 3-bit data bus. On the most right we have A0, which represents a 1, and then we have A1, which represents a 2, then A2, which represents a 4. Now the second set of inputs is the 3-bit data bus letter B. Over here at the top we have B0, which represents a 1, a B1 under the B0, which represents a 2, and then B2, which represents a 4. And these are the second set of inputs. Now over here we have the 3-bit data register letter B. So these correspond to the set letter B inputs. This is the register where the second set of the inputs is stored. Now the middle part of the schematic seems kind of confusing, and so I divided it into 3 parts. The first part is the half adder. The half adder is a arithmetic calculation, and it has 2 inputs, which makes it have 2 outputs. So it gets the 2 inputs and then it outputs the resulting calculation based on the 2 inputs. The full adder is different than the half adder because it has 4 bits and it can output a larger set of numbers than the half adder, and the same thing with the other adder. So in this middle part is where the main calculation of the ALU circuit is conducted. And finally we stop at the end of the circuit where the 4-bit accumulator register is, and this is where the final answer is outputted if an addition happened. This is a full highlighted schematic showing the path of electrons from the three different paths in the circuit. So this is the circuit that I built, and I've tried to keep the colors identical with the schematic that I showed you before, where the red still represents the 3-bit letter B inputs over here, and where the red also has the half adder, the two full adders, and then the green representing the load button, the add button, and the push button, and then finally the yellow representing the first set of inputs, which is the letter A. Over here is the 3-bit register for letter B. This is the 4-bit integrated register for the final output. This is a representation that the circuit works. So here I pressed the load button and I resetted everything, and now I pressed 1 and 1. Over here I loaded 1 and 1. Now I'm gonna add those two. So now it's a 2, now it's a 3, now it's a 4, now it's a 5, a 6, a 7, and finally an 8. And then it returns to 1, and I will explain why it returns to 1 in the end. And then here I'm repeating everything else. So now onto the problems that I faced while building my ALU. Now the first problem that I met was that there was a bug in the schematic which I did not realize and did not know about only after the due date for the ALU to be completed. And the bug was that the fourth LED, which represented the 8, could not be resetted, but it had to be saved or added to 0 to reset. So if here I'm going to reset everything to 0. So, and here I tried to reset everything here to 0, but as you can see, this is still on. And I pressed, and I'm removing the load, and I'm pressing the add. Now I'm adding it to 0, which makes it 0. And that's the way I fixed my problem with the fourth LED. Now, the second problem that I faced was the debounce. Now the problem was that the button, when you press it, it creates an after effect which makes it look like you've pressed it more than once. And the way I've fixed that is that I used a Schmidt trigger, which was given to me by my teacher, Mr. North, and that stabilized it too. But the problem was that it wasn't perfect. So as you can see, I put 1, 1, and now I'm gonna add those two. I'm gonna just press a 1, now it's 2, and now it's a 3, and now it's a 4. But look here, right now, oh, it went back to 1. So it skipped a lot of steps, and now it's 2, and it skipped, if you saw that, it skipped another step. And the last problem that I faced with the circuit was the limitation it had. And I realized after testing all over and over again, I found that each B number had its own number limit, which didn't depend on the A. So for example, for B1, for 1, the limit was 8. And it didn't matter for what A was. And the same thing for B2, for the limit was 9, and it didn't matter what the A was too. And so on until 7, where the limit was 14. And that's it, and I hope you liked the video.